Welcome to all. Today we can discuss one problem related to socket and spigot quarter joint, designing of socket and spigot quarter joint. Here is the problem. Design and draw a quarter joint to support a load varying from 30 kN in compression to 30 kN in tension. The material used is carbon steel, for which the following allowable stress may be used. The load is applied statically. Tensile stress is equal to compressive stress is equal to 50 megapascal. Shear stress is equal to 35 megapascal. And crushing stress is equal to 90 megapascal. Here given P is equal to 30 kilonewton, that's equal to 30 into 10 raised to 3 Newton. Then sigma T, allowable tensile stress, is equal to 50 megapascal, that's equal to 50 Newton per mm square. Then shear stress 35 megapascal, that's equal to 35 Newton per mm square. Crushing stress is equal to 90 megapascal, that's equal to 90 Newton per mm square. And this is the figure of the socket and spigot quarter joint. This is the front view and this is the side view. Then we can refer the KM data book, page number 65, for this the designing of the quarter joint. Designing of this quarter joint. First, diameter of the rods. How to find out the diameter of the shaft? Here, small letter d is equal to diameter of the shaft. Then, considering the failure of the rod in tension, then we can have this particular equation. We have already discussed this equation. Here, the externally applied load P is equal to this cross-sectional area of the shaft, pi by 4 d square into sigma t. Here, this sigma t is equal to, already given in this particular question, as 50 megapascal or 50 Newton per mm square. Then we can equate this area into sigma t to the external applied load. Then we can calculate the diameter of the shaft. D is equal to 27.6 mm, or we can say that's equal to 28 mm. Okay. Next, diameter of the spigot. Here this is the spigot. Spigot is the part which will penetrate to the socket, and this diameter is equal to d2. Then how to find out this diameter of the spigot? That is that we will discuss in this particular section. Then diameter of the spigot and the thickness of the quarter. Thickness of this quarter. This one is the quarter, and this is the thickness. This T is the thickness of the quarter. Then d2 is equal to diameter of the spigot or inside diameter of the socket. We can say that the diameter of the spigot is equal to the inside diameter of the socket. And T, small letter t, is the thickness of the quarter, and it may be taken as d2 by 4. Usually we can take that t as d2 by 4. Okay, here once again this equation already discussed in the previous presentation. Here we considering the failure of the spigot in tension across the weakest section. Here that weakest section is equal to, that weakest cross-sectional area of the weakest section is equal to pi by 4 into d2 square minus that small area having a cross section of a rectangle, and that area will be like this. And this area will be this one, and this diameter is equal to this small area. This small rectangular area is d2 into t, where d2 is equal to diameter of the socket, diameter of the spigot. Then pi by 4 into d2 square minus d2 into t. That is the cross-sectional area, that area of the weakest section, and that into sigma t. That into sigma t will become the external load. Then we can say, or we can find out the d2 by equating these two. Then that d2 is equal to 33.4, or we can say that is equal to 34 mm. 34 mm. The theory part is already discussed in the previous presentation. Then thickness of the quarter, T is equal to d2 by 4, that is equal to 34 by 4 is equal to 8.5 mm. Next, let us now check the induced crushing stress. Then we can check the same diameter for the induced crushing stress. We know that the load is equal to 30 into 10 raised to 3, and the induced crushing stress is equal to d2 into t into sigma c. Here that cross-sectional area, that induced crushing stress is acting at this particular area, this particular rectangular area, and that area is equal to d2 is the diameter of the spigot, d2 into t. T is the thickness of the quarter. Then d2 into t into sigma c is the induced crushing stress, where crushing occurs at this particular area. This quarter will touch, or that quarter will induce a crushing stress at that cross-sectional area. That area will become perpendicular to this front view. We can imagine that area as d2 into that thickness. That area will become perpendicular to this front view. And that's equal to here again sigma c is given, and we can find out that allowable sigma c is already given, and we can find out the induced sigma c by using this equation, that sigma c is equal to 103.8 Newton per mm square. Then we have already given that the allowable crushing stress as 90 Newton per mm square. Then we can found out that the allowable crushing stress is less than the induced one. Therefore, the dimensions of d2 is equal to 34 mm and t is equal to 8.5 mm are not safe. Most important one, the induced crushing stress is greater than the allowable one. So the calculated value of d2 and t is not safe. Then now let us find the values of d2 and t by substituting the value of sigma c as 90 or 90 Newton per mm square, or the allowable value of the crushing stress. Then we can find out that d2 is equal to this d2 as 36.5, or we can say that 40 mm. Then t must be equal to d2 by 4, that's equal to 10 mm. We can select a value for d2 which is higher than the calculated diameter, say 40 mm. Then that t is equal to d2 by 4, that's equal to 10 mm. Then this design will be safe. Otherwise there may be a tendency to fail the entire this joint by crushing. Okay, this equation is available at KM data book page number 65, equation number 4.16c. This equation, and the first equation is available at KM data book page number 65, equation number 4.16a. 4.16a. Okay, next, outside diameter of the socket. Outside diameter of the socket, we have already discussed this theory in the previous presentation, and this equation is available at KM data book page number 67, equation 4.17a. By using that equation, we can find out the value of d1. We have already found out the value of d2. Then we can substitute the value of d2 and sigma t and t in this particular equation. Then we can find out the value of d1. That d1 is equal to 49.9 mm, or we can say that's equal to 50 mm. Then width of the quarter. Width of the quarter, we can use the equation which is at KM data book page number 67, equation 4.18a, to find out the width of the quarter. That's equal to the induced, that's equal to the load P is equal to 2b into T into tau. 2b into T into tau. Here we have already know that value of T and tau. Then we can find out the B, width of the quarter, that's equal to 43 mm. Then diameter of the socket collar, we can use this equation, KM data book page number 67, equation number 4.17b, to find out the diameter of the socket collar. We have already discussed all the theory parts, theory portions in the previous presentation. Then we can find out that d4 by using this equation. That d4 is equal to 73.3, or we can say that is equal to 75 mm. Then thickness of the socket collar, we can use the equation 4.17c in the KM data book page number 65, to find out the thickness of the socket collar. That C is equal to 12 mm. 12 mm. Next, distance from the end of the slot to the end of the rod, A. This distance A. Then we can find out this distance by using the equation P is equal to 2a d2 tau, which is at KM data book page number 65, equation 4.16g. Then we can calculate that value A is equal to 11 mm. Then diameter of the spigot collar, once again this equation is available at KM data book page number 65, equation 4.16d, and this theory is already discussed in the previous presentation. That failure of the spigot collar in crushing, this one is a spigot collar, this part is the spigot collar, and crushing occurs at this particular area, this area and this area, that is in the form of an annulus, and that area is equal to pi by 4 into d3 square minus d2 square, and that into sigma c will become the crushing force, that is equal to the externally applied load. And then we can find out the diameter d3 by using this equation, which is given at the KM data book page number 65, equation 4.16d. That's equal to then we can find out that d3 as 45 mm. Finally, the thickness of the spigot collar, again that equation also available in the KM data book page number 65, equation 4.16e. And the thickness of this spigot collar by using the failure of spigot collar in shearing, we can use that equation as pi d2 into T1, pi d2 into T1. That area will become like this. That area will be like this. And this perimeter is equal to pi d2, and the thickness is equal to T1. The thickness is equal to T1. Then that area is equal to that area where the shearing occurs. Shearing occurs is equal to 5d2 into T1. 5d2 into T1. The shearing force. That shearing force is equal to the externally applied load. Then we can find out the thickness of the spigot collar. That T is equal to 8 mm. Then finally length of the quarter, that is usually taken as 4d. Then directly we can calculate that length of the quarter. Then dimension of E is taken as is the distance represented in this particular figure, and that E is taken as 1.2d. That's also we can calculate directly. 1.2d. That's equal to this 34 mm. That's all about this particular question. Then in the previous presentations, we have already discussed all the theory parts. By using the theory parts also, we can understand, or we can easily calculate all these values and design, and we can design socket and spigot quarter joint. Thank you. Thank you all.